Today I'm going to be talking to you about work that we've been doing in the Silicon Valley AI Lab, which is located in Sunnyvale, specifically to advance the state-of-the-art of speech recognition, which primarily has been advanced by better mapping neurally inspired algorithms to GPUs and clusters of GPUs hardware. And this work is all done in collaboration with the entire team, but specifically Greg Diamos, who at points in the talk I'll talk about writing custom kernels in assembly, and that's all his genius right there. So I want to give you a little background on myself. I'm happy to be back at Berkeley. I was here for my PhD in nano optoelectronics. It was actually really nice hearing Max talk about memristors because I got to do some work on that, and it's great to see the evolution of that. I made a bit of a transition in my postdoc, getting to work with Bruno and Philip Wong here working on the neuromorphic side of things, so looking on analog coding for memristors and emerging memory devices. And now I've been working with Andrew Ng in automatic speech recognition with GPUs. And so the question that came to me when I got invited to talk here is why? Because GPUs, a lot of what we've been doing here is talking about lots of neuromorphic designs and things that more specifically are emulating biology and different things. But GPUs are not really neuromorphic. They're synchronous computation. They have binary representations. At the base of it, it's just a fuse, multiply, and add in a lot of cases. But they're not quite the typical von Neumann architecture, too, because they're so distributed that there is a lot of co-localization of memory and compute. So the questions that seemed very interesting to answer were, how do we take neurally inspired algorithms and apply them to GPUs, but also what common principles exist between GPUs and other neuromorphic types of systems, and how can we learn about this? And the analogy I like to make is thinking about the gasoline engine and the electric engine, where actually both cars of both types have a long history. They were around since the beginning. But because of commercial reasons, the gasoline engine got a lot more attention paid to it. So it made a lot more advances, and electric engines were left to niche applications like golf carts and other types of things. But similarly, taking a lot of lessons from that have been made from the traditional standpoint, like vulcanized rubber and low-weight aluminum siding, you can get a breakthrough killer app like the Tesla in terms of incorporating lessons learned in both cases. So maybe there's some common principles that we can learn about here. And I think one of the key ones is that it doesn't matter if you're doing traditional or neuromorphic. We're really, since Moore's law is running out, or ran out according to Bill Daly early, with the key concept is that we always need to have coevolution of algorithms and hardware going forward. That you can't consider a new algorithm without considering how does it lay upon the hardware, and you can't consider out new hardware without considering what is the algorithm that I'm going to run on this hardware. And so that applies as equally to GPUs as it does to neuromorphic systems. And when we're taking inspiration from neural systems, oftentimes one of the biggest inspirations is this concept of distributed computation and parallel computation. And what turns out being is that the computational primitive is very important. It's very important what's going on, but perhaps equally or more important is actually the communication. And I'm not the first person to bring this up. This is a common theme that we've all been talking about. So if that is one of the issues, then we can think about what are the ways that neurons have gone about reducing these communication barriers. And one of them that's a common one is in terms of co-locating memory and compute, right? That you have your weights and your activations are all located within this single neuron. As we do things right now in a lot of computation, it's as if when a neuron wants to fire, it has to go over and talk to the other side of the brain to figure out what the synaptic weights were, which is highly inefficient. So I'm going to talk about work that we've done to reach state-of-the-art in speech recognition by sort of applying these principles, but then also going beyond there and thinking about it throughout the entire hierarchy. So thinking about your whole machine learning system from the registers of your GPUs all the way up to the file system of your cluster, and trying to balance your compute and your communication issues throughout the entire load. And then the last one was sort of also taking from the inspiration of the ideas that the brain is not randomly ordered in terms of connections, that there is clustering on different types of length scales, and due to the temporal latencies present in communication across length scales, you actually have spatial clustering leading to different types of temporal length scales of communication. And so we can see ways that this can actually be analogous to how a GPU computes, and ways that we can do that type of trick with laying that onto GPU computation. So these are sort of the three things I'm going to go through. So I want to motivate a high throughput RNNs. Bill Daly did a great job of introducing, sort of deep learning and some of the things that are advancing the field. This isn't necessarily to, advocate for deep learning. I think there's a lot of things that go good with it, and a lot of things that it has a lot of room for improvement. But one of the things that it does do right now is it has opened up a whole range of applications that aren't currently available, or weren't available to us a few years ago. And it reduces things down to a data problem, but only in the case of high throughput. So this is the Deep Speech 2 system that was mentioned. We presented this at NIPS last year, and it was sort of rated as one of the top 10 technologies of 2016. And the idea here is the speech recognition system that has primarily removed most human engineering from the problem. We take in audio. We do a slight human engineering by doing the spectrogram, although we've started replacing that as well. And we have several layers of convolution, and then many layers, 7 to 11 layers of recurrent neural networks before a fully connected layer. And we do alignment with a special cost function called connectionist temporal classification. But it basically just integrates over all possible alignments that you could get between the sound that's produced and the labels, the actual sentences that you're trying to say. So what's really interesting about the system is not many people on the team actually speak Mandarin. So we did it in English first. And all the architectural improvements that we found to improve for English, we just basically need the data. We need the inputs and the outputs. And we could do the same thing for Mandarin and get the world's best speech recognition system in Mandarin without actually speaking Mandarin. And so key to this was this idea of data scaling. And I'd love to see more graphs like this in the literature, where you have this idea that this is why neural networks work, is because they can get consistent scaling with the amount of data. Here we have a power law, or log, where we're getting a performance increase, with word error rate decrease of 40% over each decade that the data is increased, which in one sense sounds very good because it's better than your support vector machine or some other machine learning algorithm that you would do. On the other sense, it's pretty bad in the sense that it's easy to go from 100 hours of speaking to 1,000 hours of speaking. It's doable to go to 10,000 hours of speaking. We use every publicly available data set plus our own. But then to go to 100,000 hours or 1,000,000 hours of audio, these are huge training challenges. So algorithmically, it's interesting to think about ways of getting different types of scaling laws, different amounts of improvement with your increase in the amount of data you have. Similarly, neural networks scale well with the size of the network. So given our large amounts of data, we can increase the size of the network without introducing a lot of variance and get significant advantages that way. And through doing this, we could actually create a single model, not tuned to any specific data set, but we could cut across a whole range of data sets in red speech, noisy speech, accented speech, and find that we could reach similar to human level performance, and in some cases better, mostly in the clean speech area, but just with a single model. Like I mentioned earlier, it sort of reduces the speech problem down into an engineering problem of a different sort, where a data problem, where you can start to think of the data being the inductive bias into your system rather than having an inductive bias from your hand-engineered features or your choice of convolutional nets versus RNNs. The neural network is unbiased enough as it is that the data becomes your bias. So if high throughput is important, we want to think about how to efficiently implement on parallel systems. And this is, like Max was saying, this is more the traditional model of parallel processing, where you have many cores which each have their individual memories, and then they have a greater shared memory, and the bandwidth goes down as you go to the greater amounts of memory. So what you want is, for your algorithm to be great, you want to have as little work to do as possible, but then you want to be able to split it into as many independent threads as possible, requiring as little communication as you can. And whatever communication you need, you want to locate it as closely as you can to the computation that happens. But this actually turns out to be very difficult for the types of models that we care about for these systems. Increasingly deep, some of the most interesting work in deep learning is not having to do with convolutional neural nets. It's having to do with models that can learn temporal dependencies, and models that can learn to do program induction, and models that can do attention and have iterative, and they're always iterative algorithms that can iteratively refine themselves. And the problem with iterative algorithms is they're not independent. Every time you do a time step or every time you do an iteration, you need to know the outcome of the previous iteration. So in this case, what it means is that this weight matrix, it has to be reloaded for every time if we're using the matrix multiplication that we're used to. So this creates a huge bandwidth limit that we're doing mostly loading compared to computation. And as we've heard earlier today, the loading is what really takes up a lot of energy and a lot of time. So the one way of getting around this is to try to balance out your workloads. And one way that's not all of that biologically realistic, but it works for machine learning, is to create mini batches like Bill was talking about. And so what this does is it gives you more work to do per synchronization. Rather than being a matrix vector product, it turns it into a matrix product. So you're giving the processors more stuff to do in between each loading, which is great, except for that it will then bloat the memory footprint. And since we're working on these long sequences, then it's difficult to store everything into memory because you now have 64 or 128 examples per a GPU. It also complicates deployment because in a realistic system, like you said, life comes one batch at a time or one example at a time. But we've actually developed ways of batching user requests to actually do mini batches in deployment. So the fundamental breakthrough was not necessarily through designing a different algorithm, but taking the constraints of this algorithm and really satisfying all the engineering requirements, co-designing the hardware, including the design of our cluster around the requirements of this type of algorithm. And so specifically, we have a large data set, but what we want to do is to make sure that we didn't need any internode data communication. We replicated the data set on every single node. And then to get rid of any CPU to GPU communication, we made sure that every kernel that we needed access to had a GPU version. So even including the cost, the connections temporal classification cost, we wrote our own kernel to do that, which was hundreds of times faster than doing it on the CPU. But more importantly, obliviated the need to communicate back and forth between the GPU and the CPU. And then for performance reasons and debugging reasons, it was actually very important to do synchronous stochastic gradient descent versus many places like Google and others. They'll have a huge farm of CPUs and they'll just send out many copies of the model in an asynchronous manner and rely on the robustness of the algorithm to not worry about the stochastic gradient descent being out of order. But what we found is, and they would also send out, in terms of backpropagation through time, only do little bits of it at a time, such as terminating those long-term dependencies. But those long-term dependencies actually turn out to be quite important for the speech recognition task. So in order to accommodate this, what we did is we had to come up with very memory-efficient implementations of the RNNs, of the recurrent networks, because we needed to be able to store the entire utterances in a single GPU. We also needed to get the GPUs with the largest amount of global memory in order to store those utterances. The last thing was to enable a large amount of data parallelism, such that the amount of examples per GPU was actually quite low. And then that's a trade-off. So that's a trade-off in the sense that now we have a new communication, which is we have to do a lot of communication for the all reduce, for the backpropagation. We have to sum up all these gradients. And so that communication was quite slow using open source tools, such as OpenMPI, all reduced. So we had to write our own, which was about 20 times faster. And that it's sort of this game where you have to make sure everything is exactly balanced. But when it is, the entire system can run 7 times faster than it did a year ago, and a year ago was state of the art. So basically, we were taking things that were taking 3 weeks or 4 weeks to train, and then you're down to 3 or 4 days to train. And so that drastically changes the type of thing you can do. And all of a sudden, you can do twice as good because you can use, twice as much data or 10 times as much data. Okay, so this was the key to landing the deep speech to technology and making it actually work. But I wanted to sort of go beyond there, because I was just talking about the hierarchy. But we want to start thinking about the GPU itself in terms of how can we better co-locate memory and computation. And it's interesting because this is a common thread that we see in neuromorphic computing, also the things like stuff coming from Micron's perspective in terms of coming from the memory and thinking about embedding compute. Here we're coming from compute and embedding memory. And what's nice is that GPUs have a lot of distributed memory present. So this is sort of a very rough sketch of a Titan X GPU, but it has 24 of these cores, or streaming multiprocessors, and each one of them has 128 threads. And each of those threads has its own designated memory. And so what you see here is a graph of the bandwidth and the amount of memory present. So this is the amount present within a thread. This is the amount present within the core. And this is all the cores, so communicating between cores. And then there's a greater DRAM out here, which is the global memory, which has a huge amount, right? You're up in the gigabytes amount. So that's where we can store our data. But so there's no way to store the data within the registers of the actual threads. But what it turns out is if you are actually using all of these cores efficiently, you actually have a fair amount of memory that you can use while locating all of the weights in the threads themselves. So what this means is that you've removed the need, your iterative dependency, you've removed it. You're now storing the weights in the registers for the entire length of all the time steps, hundreds of time steps. So instead, you just launch it as a single kernel, and it can just run. Now the thing is, you're limited by, this is intimately tied into the design of the hardware. So the most we can do, it limits us in the size of the network we can do. In fact, we can't do larger and we can't do smaller. All of our networks have to be 1152 because that's exactly what fits into the memory design of the kernel. And this had to be written in assembly in order to make this work, but hopefully CUDA will evolve to allow these types of things with the next generations of processor. And this memory space here, the thread memory space, is really going to increase in future iterations. So hopefully this type of design, of thinking about designing in the registers, will become more popular. And so what does this buy us? This a huge speed up. So we can go, in terms of the RNNs, over matrix multiplies, we can now go 30 times faster. And that you can see that the amount of teraflops we achieve is actually proportional to the amount of time steps in the utterance because you're increasing the amount of work. You're not launching a single kernel for every iteration. You now have the kernel is across all iterations. So you actually get much more efficient for the longer utterances, which is matched to the problem that we're interested in. So you have this, once again, all the way down from the algorithm to the implementation. So this is over even the fastest matrix multiply kernels from Nirvana at the time. And what's interesting as well is that it allows us, since we're no longer relying on mini batches to provide the amount of work to work on, we can now go to very low mini batches, which are much more biologically realistic and also much better for deployment. And so you can see here's the scaling of matrix multiplies as a function of mini batch size. And obviously Nirvana is better than the cuBLAS, but it doesn't really, it's a sort of a different league of operation. Here at a mini batch of 4, we can achieve peak efficiency. And what's also great is that also for thinking about data parallelism, the graphs that Bill was showing were not 100% they were showing weak scaling in the sense that the amount of work was scaling appropriately, but the convergence time of the algorithm doesn't necessarily scale because you're having to increase the mini batch as that happens. But in this case, you can increase the number of GPUs per given mini batch. So we can run those 128 GPUs and actually go 128 times faster for solving a single experiment, which is helpful in the design process of deciding which network architectures and stuff. You have a lower latency to help to figuring out what that change that you made to the architecture actually, what impact did it actually have. So the last thing I wanted to talk about was taking the same idea and we wanted to extend it to the case where we have this local communication within the registers, but we don't. Right now, we're doing all-to-all communication when we do it when we're stashing all the weights on the chip. But inspired from sort of the connection between local connectivity and sparse temporal connectivity, we can imagine a situation where we have, let's say, like a block diagonal. So you can imagine this as a bunch of clusters of neurons where they each can communicate with each other on a very fast time scale, not subsampled at all. So every time step, they're updating each of their weights. So there's several neurons in here, and they're all communicating with each other. And then you can have a global communication that could be reflecting the larger size between the clusters. And so this all-to-all communication, you can then schedule at more longer intervals. And this is something people in deep learning have been exploring not for system reasons, but for an inductive bias that they feel like might be better suited to certain problems. Like the clockwork RNN was a classic example of such a thing. But here the difference is we're explicitly changing the algorithm to match the hardware as well, because these types of local communications are better suited compared to the global one. And so what we find is that as we do that having the presence of the local connections over not having presence of the local connections, so just the global connections subsampling, can actually give a significant advantage because because in the problem domain that we're interested in, there's a lot of processing that only needs to happen in the cluster scale, and the global communication only needs to happen on smaller length scales. And so that sort of brings me to the end of the talk, and I'll just come back to say the exact same things I said in the beginning, which was given that communication is a major cost in distributed algorithms, we found that we can advance the state, that deep learning can really benefit from this hierarchical understanding of balancing communication and computation, that co-locating even down to the level of registers can increase RNN and iterative algorithms by at least a factor of 30, and that matching algorithmic sparsity with hardware constraints can also significantly lower communication costs. So I want to thank Greg and the rest of the Sveil team. This is a little bit of an old picture. We're now actually 50 people. But yeah, and I want to thank you all very much. I'd be happy to take questions.
Thank you very much for this nice talk. There's a question there.
Thanks for the talk, Jesse.
Mm-hmm. No problem, Jesse.
I have two questions. The first one is, do you find that you're kind of like less sensitive to hyperparameters that like aren't topological ones, so like weight initialization or like the parameters with momentum or something like that, because you have like more data than anyone else in the world? Maybe I'll ask them one at a time.
Yeah, I don't think that's actually the case. So you would think, yeah, so the data would be reducing the variance, right, so that we would maybe be getting less sensitive to variance from a lot of the hyperparameter tweaking. And it seems like for most cases, the hyperparameters will not ruin your performance. But if you want, you can always get an extra 10% out if you really tune it very, very nicely. And I think what people are learning in deep learning is just all the tricks that we can do to optimize these problems better are actually quite essential. So, batch normalization. I didn't talk about it, but batch normalization was actually key to this work, and other types of tricks like that, skip connections, all those types of things.
Then the second one, have you done like any sort of like psychophysics sort of experiments on the network? Like if you kind of block out phonemes with white noise or something like that, can it like kind of infer what was being said based on the context?
Yeah, so we haven't done that, but I have done a lot of, what's interesting is most of these models are broken up traditionally into an acoustic model and a language model. And the acoustic model models the phonemes, and the language model models how the phonemes go to words. But here we're going directly to the characters of the alphabet. And what's interesting is as you add more data, it goes from sort of phonetically spelling things out, and then it starts to learn how to spell things correctly. And then it even goes to having an embedded language model where it learns that the difference between two and two, where TOO and TWO, depending on the word context surrounding. So that's, I think, where we have a lot of these long-term dependencies coming in. And this sort of goes to an earlier question that was asked about the bottlenecks of deep learning. And I think one of them is this concept that end-to-end learning is fine and great if you want everything to be inside the system. But interfaces are really good. Strongly typed interfaces are very good. And the fact of the matter is we're learning a language model based on the language present within the training set, which is much less than the language available to us elsewhere. And so it's not, we would prefer to learn a language model on all that. And so it's actually, and this is a case where end-to-end learning is actually hurting us rather than helping. So having deep learning where you can learn to define those interfaces, not have the algorithm define the interfaces for you, but have intermediate representations that you can then plug in modules together and engineer bigger systems. I think that's a challenge for the field.
Thanks.
Okay, so let's thank the speaker again. And